5 broad areas of physics that I think you should know a little bit about: classical mechanics, energy and thermodynamics, electromagnetism, relativity, and quantum mechanics. The ideas around energy came about 100 years after Newton. It may be the most important idea in physics. Energy is not a vector like force or momentum. It doesn't have direction, but it is a number. Work is closely related to energy. It has the same units. Work is force times distance traveled. 1 Newton times 1 meter is 1 joule. If you lift a small apple 1 meter, that takes 1 joule of energy or work. Energy is really a measure of how much work you can do. Work is simply transferring energy from one form to another. Energy for most objects consists of kinetic energy plus potential energy. Kinetic energy is the energy of motion. It is expressed as 1/2 times the mass times velocity squared. The more mass you have and the more velocity you have, the more energy you have. Velocity makes a bigger difference in energy than mass. Going from 80 miles per hour to 60 miles per hour reduces your car's energy by almost 50%, which means that in an accident, you have a much higher chance to survive going 20 miles per hour slower. If you're carrying your phone and you accidentally drop it from rest onto concrete, your phone is probably going to get damaged. But where did the energy come from to damage it? The phone had what is called potential gravitational energy when you were holding it near your ear. The potential energy was converted to kinetic energy as it fell. Gravitational potential energy is expressed as mass times the gravitational acceleration times the height. This is really another way to express force times distance, or work. This potential energy gets converted to work or a force acting on the glass which breaks it when the phone hits the floor. So the total energy of an object is both kinetic energy plus potential energy. Potential energy can take many forms. Gasoline or petrol, for example, has chemical potential energy. The biggest thing you should remember about energy is that it's always conserved. It's not created or destroyed. It only changes form. Now, talk about energy leads naturally to thermodynamics, which is the study of work, heat, and energy in a system. The biggest concept worthy of remembering is flow of heat. We defined energy as how much work you could do, but another form of energy is thermal energy. If a car is moving and you apply the brakes, the kinetic energy of the car becomes zero. Where did that energy go? It didn't go to gravitational potential energy, and it's not stored in the car somewhere. Did it disappear? No. It was converted to thermal energy, created by friction of the car's brakes. Heat is a flow of thermal energy from one object to another. Thermal energy created by the brakes raises the kinetic energy or movement of molecules in the air. This results in a temperature increase of the surrounding air. This is ultimately where the kinetic energy of your car ends up after you come to a stop. The temperature of a system is the average kinetic energy of atoms in the system. Thermal energy is the total amount of kinetic energy of atoms in the system. Another concept in thermodynamics is the idea of entropy. Entropy is a measure of disorder, but more accurately, it is a measure of the information required to describe the microstates of a system. The second law of thermodynamics states that the entropy of an isolated system can never decrease. If you put 2 liquids together in a bucket, and one is very cool and the other is very hot, why can't you get it such that the cold part gets colder and the hot part gets hotter? Energy could still be conserved because the decrease in thermal energy of the cold water could be offset by the increase in thermal energy of the hot water. The reason this does not happen is because of the second law. The universe is on an inexorable path to higher and higher entropy or more and more disorder. Practically, what this law tells us is that some energy is more useful for doing work than others. Energy at lower entropy can do more work than energy at higher entropy. For example, the energy stored in gasoline is more useful for doing work than the thermal energy that is dissipated from the brakes of your car. An orderly energy is more useful than one that is less orderly. The heat and exhaust from the car will not spontaneously rearrange itself to become the gasoline, but gasoline can be converted to heat and exhaust. It's important to remember the words isolated system. If you put a glass of water in the freezer, it will decrease the entropy. But the inside of the freezer is not an isolated system because the refrigerator uses energy from electricity to cool the inside. It increases entropy of the room by heating up the room, more than cooling what's inside the refrigerator. You should also remember this fact. The one-way flow of entropy appears to be the only reason we have a forward direction of time.